Hello, good morning to everyone. So we were discussing about the basis sets. So in last lecture we have discussed about the last few lectures actually we have discussed about the basis set and their types, and also we have seen the nomenclature and number of basis functions for a particular basis set. In this lecture, we'll discuss a little bit different things, like that when your systems will not be in ideal cases, like if you consider a single water molecule, then your electrons are distributed ideally, like electrons will be in oxygen and hydrogen. But if you put there some salt like NaCl, so what will happen that sodium, you know that NaCl, this can dissociate, and Na plus and Cl minus both can stabilize by hydrogen by water molecule. So what will happen that Na plus will polarize some of the electron density of oxygen towards sodium, whereas hydrogen will polarize some of the electron density of the chlorine towards hydrogen. So these are not actually ideal cases. So what actually difference here, that your electron density is actually distributed little more beyond the nucleus, and it is actually more flexible. Okay. So what we have to define the real system, we have to add few more basis functions on the basis sets, okay, other than the already available functions. So let's discuss one by one that a few considerations, that polarization functions. So the basis functions should be sufficiently flexible because the molecular orbitals, which are actually the eigenfunctions of Schrödinger equation involving multiple nuclei at various positions in space, require more mathematical flexibility than do the atoms, because in molecule there can be some polarizations of the electron density towards the negative to positive end. Okay. So because of the utility of atomic orbital like GTOs, the flexibility is almost added in the form of basis functions corresponding to the quantum number of higher angular momentum. Okay, means that if you know when angular momentum becomes higher, your the flexibility of the electrons to become more higher. So what we have to do, we have to, if we want to add define the polarization phenomena, or we want to replicate the polarization phenomena in our basis set, then what we have to do, we have to add more functions which have the higher angular momentum. So for first row atom, the most useful polarization functions are DGTOs, like they have the highest level is the p orbital. So the next higher angular momentum orbitals are d. So we have to add d type wave functions for the polarizations. For the same way, for if you want to add the polarization function of hydrogen, then you have to add a p-type GTOs, because that is the next higher angular momentum functions. So polarization functions, actually Pople and co-workers introduced a simple nomenclature scheme on their basis sets, that you have seen the nomenclature in last lecture. So they have added another functions with the form of star, and that is, we said the we pronounce it as a star. Okay. So the 631G star implies a set of D functions added to polarize the P functions in 631G. So 631G is the basis set without polarization, and you know this is the basis set of a double zeta. So if you add one star, then there will be the polarization functions for the heavy atom will be added. A second star means your polarization functions will be implied on hydrogen and helium, that is for the first atom. So now we can see that how many functions will be now there. So 631G, if you consider 631G, then your core orbital is only one function, and your valence orbital will be splitted by two sets. So this is 2s prime 2p prime 2p double prime sets and double prime set we have expressed. So if we do not have star, then your basis functions will be 9, that you have seen. Now you have to add the polarization functions for the valence shell. So for the this, as it's the next angular momentum wave function is the d. So what you have to do, that you have to add 6d functions here for the polarization. Okay. Now why 6d is coming? Because this is coming from the Cartesian d orbital calculations. But if we use the spherical harmonics problem, like if we use the r theta phi coordinates, then we will have the 5d orbital that you have seen in the Schrodinger equation. When we solve for hydrogen atom, we got for the 5d orbital, but in case of Cartesian calculations, you will get the 6d orbital total. Okay, so this doesn't matter, but we have to add one more a few more functions as a polarization function. So if you want to consider say pictorially, the things are that you have a p functions and this is d functions. Then when we combine that, this will have the take the shapes like this one, means that your p functions is now little more flexible and take some little bigger space to the outside. Okay, so this can explain the polarization in this way. Okay, so another cases is that for the core electrons and bonding electrons, you know, they are tightly bound and they are bound to near about the bonding or nucleus. But if you have lone pair or if you have some negative charge, that can happen, because like if you consider the H minus hydrogen negative ion, so H minus you know, if you search the size of this H minus, then you will find out that H minus has more than chlorine even. Okay, so means that if you only consider the basis function, normal basis function, that is the 631G, like that, only a single basis function or two basis functions for that orbital, but that can explain the hydrogen atom, but it cannot explain the hydrogen H minus, because in H minus the electron density is very much diffused to the outer from the nucleus. So what you have to do for these cases, you have to add another functions to replicate the diffuse chip electron cloud, which actually available for in case of lone pair, which is not tightly bound, or in case of anionic systems. Okay, so these expanded electron clouds are found in molecules of anions, or in case of electronically excited states also it's possible. So to address these limitations, we'll have to augment, means we have to incorporate another functions that we said diffuse function, means to express the diffusive electron cloud. Okay, so diffuse functions in Popple basis set was added by a sign, that is plus. So then 631 plus GD indicates that this D means actually this let's me explain one more time that what is this D. This D means 1 star. Either you can write this as a D or 1 star, or D slash P means that either a double star or DP. You can write, you can use both the symbol. For example, if 1 star means that you are adding polarization functions for heavy atom, means that you are adding D functions. But if you are adding double star, means the next star implies that you have to add the polarization function on hydrogen or helium atom. That means you have to add the P functions. For that, either we have used the star or we have used DP. But diffuse function is indicated by one plus function. Okay, so if there is only single plus, means that heavy atoms have been augmented with an additional one S and one set of P functions having small exponents, and a second plus indicates that the presence of diffuse S functions on hydrogen atom. So particularly for the calculations of acidities and electron affinities, diffuse functions are absolutely required, because you have to replicate the electron density properly. For instance, if you consider the acidity of hydrogen fluoride increases by 44 kilocalorie per mole when the 631 plus GD basis set is used instead of unaugmented polarized function, that is 631 GD. Okay, So to replicate the acidity or so many properties like electron affinities for diffusion functions are absolutely required. So now we'll see how we can include more basis function here. So let's consider the 3 to 1 plus g basis set, means one extra one extra diffuse functions are added here, means that you will have the same way you can the 3 to 1 g functions. So 3 to 1 g is like this up to these functions, and we make a red block which are the extra diffuse functions. Okay, so 2s prime, 2p prime, 2p prime. So a set of s and p functions we have to add to replicate the more diffusive electron cloud. And here if you add both simultaneously, that diffuse function as well as polarization function on carbon, then you have to add this 3D series for polarization function and this series for diffuse function. So in all the cases you have seen that when you do not have plus, then you have 9 basis functions. When you add plus, you have 13 basis functions. Again, when you have added star, you will have 19 basis functions. So it means that when you are adding more and more basis functions, means that you will able to explain more and more realistic phenomena, but the same way your time will be more time will be required to do the computation. Okay, so these are all very important things to understand the calculations. That's method we have already discussed a little bit, and the basis set now. Okay, so next is that what we have discussed much times of the Popel basis set. So other than the Popel basis set, there are another class of basis sets developed by T.H. Dunning Jr., and these are called correlation consistent basis set. So these basis sets are a little bit more complicated, and they are actually mostly designed for the post-Hartree-Fock calculations, where electron correlation is better taken into account than at the Hartree-Fock level. In our next class, we will discuss about the post-Hartree-Fock method. So these basis sets are intended ideally to give with such calculations with improved results in step with their increasing size. Okay, so they are called actually correlation consistent basis set. Means that when you are incorporating the electron correlations consistently, your basis sets will be higher, so that your calculations will be more reliable. Otherwise, if you are incorporate electron correlation phenomena more explicitly, but your basis set you do not increase, then that will be a controversial thing, that you that will not able to explain that your basis set is not so much flexible to explain the electron correlation phenomena. So you cannot actually, that calculations will be not perfect. So what you have to do, you have to incorporate your size also, increase your basis set size along with the electron correlation. So for that, it is actually called that correlation consistent basis set. Ideally, they systematically improve results with increasing basis set size and permit extrapolation to the infinite basis set limit. So we can use more and more basis sets to the infinity. So this set basis sets are written as like CC, and that CC sets, CC for correlation consistence, and CC sets are designed for CCpv xz, where x is P stands for the polarization function, V stands for valence, X is the number of cells the valence functions are split into, and Z for zeta. Thus, for if we consider CCpvd basis set, we will pronounce it as correlation consistent polarized valence double zeta basis set. Or CCpvd, where we will pronounce that, will define it as correlation consistent polarized valence triple zeta basis set. Okay, so in this way, this can be quadruple zeta basis set, or it can be 5 zeta basis set, 5-fold split basis zeta basis set, or it can be anything more extra. Okay, so the number of basis functions on CH2 you can calculate the basis functions also, but it is not actually so easy like the Popel basis set. So you can just compare few things for like CH2 molecule or CH2 system. So you have one carbon atom and 2 hydrogen atoms. So if you consider CCpvdz, so how many basis sets will be there? Because it will be total 24 functions. So you can these are all given in Errol-G. Lever's books, how they can calculate. So for as it's the polarization double zeta, means that you have the hydrogen atom will have total 5 basis functions, means that your valence shell will be splitted by 2. Along with, you have to incorporate the as double zeta, means 2 orbitals for you have to for 1s orbitals you have only for hydrogen, so you have to add two basis functions for the this. And if you add incorporate the uh, polarization functions, then you have to add the 3p functions. So 1 s orbital will be splitted by 2 due to the double zeta basis set, and there are another set of p polarization functions, that is 3p will come. So total 5 basis function. So for hydrogen it will be 5, and for carbon you will get for 9 is normal, but if you had the polarization function, so you have to, if you add the 5d function, so there will be 14. So there are 24 functions total here. Okay, so here you can remember that this we have used 5d functions. So sometimes we add also 6d, or sometimes we add the 5d. So that actually depends on the program, which program we are using. We have to see that what type of basis functions that they are using. Okay, so thank you very much. We'll next lecture we'll discuss about little more about few basis set errors and few more important things.